This is the original gear out of the mainspring arbor. You can see that the teeth are pretty shot. It's supposed to look like this. So there's a good gear. And I've disassembled the mainspring arbor. That's where you wind it with the key. I've disassembled this so that I can take the old gear off and put on this new one. This is out of an original ITR clock also, same type. So I'm just going to reuse it. I couldn't reuse the whole thing with the arbor because the arbors on this one are a different shaft size. There's some slight differences, so I had to take this completely apart in order to just use the gear by itself. And the clicks are a little bit different, but they'll still do the job. To rewind the mainsprings, I've mounted the arbor in my lathe with a rod coming out of the tool post. And then I'll wind it up. And once the spring is down small enough, then I can get a hose clamp around it to hold it. The new replacement gears are installed, and I had a small problem in that the diameter of these gears is about 60 thousandths of an inch smaller than the old original gear. So that would mean that this gear meshing up with the next one inside, the teeth would not mesh as deeply, and that's a problem. So I had to make new bushings here, and I bought some 642 alloy bronze. This is bronze, not brass, so it's a little bit harder and it'll wear better over time. I made new bushings, and if you can tell, there's more distance here than there is around on this side. I purposely drilled the hole in this bushing offset by 30 thousandths of an inch so that it pushes this gear 30 thousandths of an inch more towards this next gear that it's driving, and causes the teeth to be properly meshed. Problem that caused by moving this 30 thousandths over is that when I put this next piece on, and then this is a winding limiter, each time you wind and it goes around and this little peg here falls into a hole, it indents this one click at a time, and then this shows, it comes through the front dial and it shows you how much wind you have. As you wind it, it goes up and up and up, and this little indicator pointing through the dial goes up and tells you got a full wind. Anyways, when this gets all the way up to here, it stops, and this protrusion here stops so that you cannot overwind the clock. It gets this far and then stops. But now the problem with moving this gear 30 thousandths in that direction is that where this center hole is, now there's this 30 thousandths of an inch gap here, and that shouldn't be. It needs to sit and right in there with very little space. So what I'm going to have to do next, this is the original shoulder screw that was in there. I'm going to make a new shoulder screw with the actual shoulder itself, the flat part, not the threads, but the shoulder part that sits in here, that'll be offset by 30 thousandths, so that instead of this sitting here and having some play, it'll go up like that, and everything will be back to the same right amount of clearance. A lot of work just because I couldn't get the exact same diameter gear. Even though these gears are out of an 88 beat ITR movement, gears are slightly different. And now that it's back together, you can watch this cam turn as this pin goes around and falls into the grooves. Here it's coming around, it's right underneath here, and it'll push this and advance right there. And that keeps going until you get all the way to the end that's fully wound. This time clock has a rarely seen feature, which is an alarm or bell ringer hooked up to the timekeeping train. This is the alarm right here. There's a set of electrical contacts with wires that go up and out of the case. I've mounted a bell on top. The way these contacts work, the actual electrical contacts are right there, and this blade actually is two blades. If I move the one in front, you can barely see the one in back. And one contact of each side is connected to each of the blades. You have this little cog or this little block that is set right at 8 o'clock in this example. So as time goes by, you have 7 o'clock in the morning, then 8 o'clock. And where I've set this at 8, as 8 o'clock comes around, it pushes both of these blades up at the same time, but one blade is just about 2/1000ths of an inch shorter than the other blade. So as it gets right to the very tip of that block, one blade will fall first off the edge right there, and as it fell off, it closed the contacts, so now the bell would be ringing. Here you can see the contacts are closed and the first blade is fallen off, and as I go a little further, the second blade will fall off, and that opens up the contacts again. Now the rate at which this wheel turns, the contacts will stay closed for about 10 seconds or so. If you have an example like here at noon, you want people to punch out in a certain window, like let's say between 5 minutes right before noon, you come up to here and you have this second type of block that has 2 notches on it, or 2 steps. So you get about 10 seconds of ring right there before, yeah, it went too far, they both went at once, but you get a ring there and then you get another ring about 5 minutes later. So in this window between about 5 minutes worth of time is when you're supposed to clock out and go to lunch. Here's the dial face, and you can see the wind indicators. Little red that would move up and down. When they get down here, time to wind the clock. An example of a card holding rack. Employee number 200, that's where your card belongs. If you worked in the payroll department, you had one of these. And they were used to help you figure out how much you pay the employees. You slide this in and out, find the amount of time. There the employee worked exactly 7 hours, and if they made $2 an hour, you paid them 14 bucks. That is the International Time Recording Clock from the 1920s. Thanks for watching. For more information, visit GameRoomRepair.com.